Welcome back to your second day of online instruction. Today is week 11, day 1, scheduled for release on March 30th, and we're going to be talking today about simple AC circuits. Just a brief note, I've made some slight changes to the syllabus schedule for this week. Today, Monday, we're going to just cover sections 1 and 2 out of Volume 2, Chapter 15, and on Wednesday, in the same chapter, we'll do sections 3 and 6. Then Friday, we'll be doing a brief overview of Chapter 16, kind of just some of the high points and big ideas in Chapter 16. Also, Quiz 9 is due today, so if you haven't got that turned in already, by 10 a.m. Earlham time, let me know so that you can request a late pass. So with all of that in mind, we are ready to go on to talk about AC circuits. So to know what AC circuits are, we need to contrast them with the types of circuits we've been dealing with so far. So far, we've been dealing with something called DC circuits, where DC stands for direct current. And what this means is that the voltage applied to the circuit and the current flowing in the circuit are constant over time. So that might look something like this on a graph. So both the voltage and the current are constant over time. So these lines are intended to be straight. We're going to contrast this with what we're going to learn now, AC circuits, where AC stands for alternating current. This means that the current switches from flowing forward to backward to forward to backward continually over time, usually following a sine wave pattern. So a corresponding graph for an AC circuit might look something like this. Where both the voltage and the current vary over time. So at the beginning here we have positive voltage, meaning the battery is oriented some direction, and it sends current through in that same direction. But a little bit later, the voltage of the battery becomes negative, which effectively means that the polarity of the battery has reversed. So if the battery was originally oriented like this, then later the battery acts like it's oriented like this, switching back and forth regularly as time passes in the circuit, and that means that current will flow in an alternating direction as you go. So these are the types of circuits we're going to start dealing with now, AC circuits, where the voltage applied to the circuit is called little v as a function of t, which I would think of as the AC voltage, is some maximum value V naught times sine of omega t, where this value here, the maximum value of the voltage, is V naught. The current will also follow a sinusoidal pattern. Will have a similar formula that will be given as little I of t for the AC current, the current at any given moment. And this has a similar form of an equation, the maximum value I naught times sine of omega t, where I naught would be the maximum value of that green current graph. So the most common example of AC circuits we have is the AC circuits we have here in America, our wall outlets. And with any AC circuit, we need to know both the maximum voltage V naught and the frequency with which the voltage switches back and forth. So for wall outlets in the US, V naught is 170 volts, and omega is, well, you may have heard that wall outlets in the United States are 60 hertz, but this is a regular frequency, not an angular frequency. So if we take 2 pi times the 60 hertz frequency, we get 120 pi radians per second is the omega value, or the angular frequency for power outlets in the United States. Now, some of you might be a little confused here because you might have some advanced knowledge of this. You might say, well, Brennan, I thought that wall outlets in the United States are 120 volts. And to an extent they are. 170 volts is what's called the peak value of the voltage. I0 and V0 in general are both peak values. There's also something else called the RMS value, and this is what the 120 volts is. And that 120 volts is called the RMS voltage, or the root mean square voltage, where any value's RMS voltage is just going to be its peak voltage, or peak value, divided by the square root of 2. And you could make the same relationship for the current. The RMS current is equal to the maximum current divided by the square root of 2. And what this basically is effectively an average current, or an average voltage over time. So you'll want to make sure you know whether you're talking about the RMS voltage of a circuit or the peak voltage of a circuit. So they are very similar but slightly different quantities. We're now going to discuss how an AC power supply interacts with our three circuit elements that we've learned: resistors, capacitors, and inductors. So first, we're just going to look at an AC resistor circuit. And an AC resistor circuit might look something like this, where we have our resistor over here with a resistance of R, and our AC power supply that supplies a voltage of V0 times sine of omega t volts. This little circle with the squiggly line in it is an AC power supply. Which provides a sinusoidal voltage. So the voltage would look a lot like this, but a better sine wave. So when we're dealing with this circuit, we have an AC circuit, and all of our normal circuit rules still apply. We still have to spend the battery voltage. So our battery voltage must be equal to our resistor voltage, which is equal to V0 times sine of omega t. And then Ohm's law still applies, so we still have that the voltage across the resistor is the current times the resistance, from which we can use to find the current through the resistor, lowercase I, specifying that this is an instantaneous value as a function of time, will be equal to the resistor voltage as a function of time divided by the resistance, which is constant, which gives us V0 over R times sine of omega t, which we will call I0 sine of omega t. So to get an idea what this might look like, we're going to draw a couple graphs here. One of them is the graph that we drew on the previous page, the graph of how the voltage and the current look over time. The voltage will follow a sine pattern. So to within my ability to draw things, this might be what the voltage across the resistor looks like, where this value here, the maximum value, is V0. And then the current will follow a similar pattern. Current is also a sine function. So to within my ability to draw these two things lined up with each other, we have V0 and I0 as our maximum values, and the current through the resistor and the voltage across the resistor as these two graphs here. One thing I want to note about this diagram right here is that for a resistor only AC circuit, the current and the voltage, both through the resistor, peak at the same time. This will turn out not to be the case in the other circuits we consider, but resistors are the simplest circuit elements, and if we apply an AC voltage to a resistor-only circuit, anytime the voltage, either across the resistor or the voltage of the battery, their equivalent, is at its peak, then the current will also be at its peak. When the voltage is at its trough, the current is also at a trough. When the voltage is at a zero, the current is also at a zero. Now there's another way we can represent the voltage and the current in AC circuits, and that is something called a phasor diagram. And on a phasor diagram, we have two axes, kind of like X and Y, and we represent each of our AC quantities, like the voltage and the current, as vectors on this two-dimensional space. So for example, V0, whatever the maximum voltage of our AC power supply is, can be represented as a vector on this two-dimensional space. And that vector is going to rotate around, keeping its tail at the origin, but transcribing a circle as it moves around this phasor diagram, where this angle right here is omega t. So as time gets bigger, this vector will rotate. So at some time later, V0 would be here, and then here, and then here, and then here, and so on, all the way around the circle, continuing to rotate with time. Then, if we don't want to know what V0 is, but rather we want to know V of t, the voltage across the resistor at a specific time, we just take the y component of this vector. So right here, where the projection of this vector onto the y-axis ends, this is going to be the actual voltage across the resistor at that time. So if you think about this, as the red V0 vector rotates around, the point where it intersects with the y-axis right here is going to go from positive y to 0, down to negative y, back to 0, then positive y to 0, and back down, and it will alternate, oscillate back and forth, just like AC circuits should. We can also put the current on this same graph. So in green, this green arrow right here could be I0. The magnitude of the vector is the maximum value of that quantity. And then the y component of that vector gives you the value of that quantity at that specific moment in time. So here, I'm going to draw the green one in a little darker, make sure everybody can see it. We have the two vectors are right on top of each other, rotating at the same rate. So, similar to what we saw before, we can say that, should really use the appropriate notation, the current through the resistor as a function of time, and the voltage across the resistor as a function of time, peak at the same time. This new diagram, the phasor diagram, might not seem like it's really helping us much, but it will turn out to be a very helpful way to visualize things for AC circuits, especially when we have multiple different circuit elements at the same time, like we're going to talk about on Wednesday. But just as a reminder, each of these vectors represents the maximum value of that quantity, and they are constantly rotating around this diagram at a rate of omega, and their y components give you the value at any specific moment in time. So, this is resistors, and now we're going to see what this looks like with other circuit elements. Next one up is going to be capacitors. So that circuit is going to look like this, where again, the voltage of the battery is V0 times sine omega t, and the capacitance here is just going to be C. So following along with what we did before, we will want to know the value of the voltage across the capacitor at any given time. So since the voltage from the battery has to be spent at the capacitor, then that means the voltage across the capacitor at some specific moment in time is the same thing as the voltage across the battery at some specific moment in time, which is capital V0 times sine of omega t. Well, now we also have a formula that we've used before, that the charge on a capacitor is equal to the voltage on that capacitor times the capacitance. So applying that formula to this situation, we have the charge at any given moment in time is the voltage across the capacitor at any given moment in time times the capacitance, which is constant. So the charge on the capacitor as a function of time is C times V naught times sine of omega t. Eventually we're going to need to know the current though, and we can find the current here by remembering that the current is just the rate of movement of charge. So current is literally the derivative of charge with respect to time. So we can take the derivative of this function right here, and we get our constants C and V naught stay out front, leaving a little room. Derivative of sine is cosine of omega t. Chain rule times the derivative of what's inside brings the omega out front. So this is the formula for the current as a function of time in the circuit, which will often be written again as I naught times cosine of omega t. But sometimes it's easier if we keep all of our oscillating aspects of this circuit in terms of signs. So we can rewrite this cosine in terms of a sine as I naught times sine of omega t plus pi over 2. Note that this is in radians on the inside of that sine function there. So what this means, first I want to define one particular quantity, and that is something called the capacitive reactance. Capacitive reactance is given the variable xc, and it's a lot like the resistance, but just for the capacitor, because we define it as V naught divided by I naught, which for this particular type of circuit is 1 over omega times C. Capacitive reactance is a lot like the resistance for a capacitor. It even has units of ohms. But when you see capacitive reactance, think of the following. Think the opposition of the capacitor to changes in current. So the higher XC the capacitive reactance is, the more capacitor will oppose changes in current. The lower XC will be, the more open the capacitor is to changes in current. So, with all of that written down, let's make the graphs we've been looking at again. So one of them is just the graph where we actually plot voltage and current versus time. The voltage as a function of time is still our sine wave, where this is Vc as a function of t, the voltage across the capacitor as a function of time, with maximum value V naught, and that is a sine function. But my current is equal to a sine of omega t plus pi over 2. So remember from way back at the beginning of the course that a phase shift of positive pi over 2 slides the graph to the left by pi over 2. So we actually get, for current, something that looks like this. We start off at our max, we hit our 0 here, and we hit zeros at the opposite times that the other graph is hitting zeros. This shouldn't actually be getting smaller over time. That's just my lack of ability to draw things clearly. So this is the current in the capacitor as a function of time with maximum value I naught. So note that unlike our resistor graph, the current and the voltage across the capacitor and through the capacitor do not peak at the same time. Time goes on as you move across to the right in this graph, so kind of following my cursor along, we'll see the current hits its maximum voltage here at this time, and then the voltage hits its maximum here at this time. So we could say that the current peaks before the voltage. So if we had a voltmeter and an ammeter hooked up to this capacitor, we would see the current reach its maximum value, and then the voltage reach its maximum value, and then a brief pause for the rest of the cycle, and then that same thing repeats itself. And we can represent this same information on a phasor diagram, where we have our two axes again, and we can draw both of our vectors on here. So one of those vectors would be V0, the maximum value of the voltage across the capacitor, which is equal to the voltage across the battery. And like all good vectors on phasor diagrams, this one is rotating at an angular speed of omega, which means this angle right here is omega t. But for a capacitor, we no longer have our current lined up with the voltage like we did for the resistor. We'll turn out the current arrow, that was terrible. We'll point out this direction, where this vector again is I0, the maximum value of the current. So I'm going to make this arrow just a little bit longer, not to represent anything physical, just to make my diagram a little cleaner, where this angle between the two is 90 degrees. And again, like before, the projection onto the y-axis, or the y component, gives you the value of that quantity at a specific moment in time. So that would be the voltage across the capacitor at a certain moment in time, or the current through the capacitor at a certain moment in time. So when you get to this point, looking at this phasor diagram, remember that both of these vectors are rotating at a speed of omega. So they will maintain that angle of 90 degrees between them and continue to rotate around. So as they rotate around, you'll see that the current will cross this y-axis first, followed by the voltage. So again, even on the phasor diagram, we will see that the current peaks before the voltage. So just one more reminder here, while I'll keep saying them, but each vector is the maximum value of that quantity. The maximum value of the voltage across the capacitor, the maximum value of the current in the capacitor, also the current in the whole circuit. And these vectors rotate around our phasor diagram at a constant rate omega, the same omega that is part of our AC power supply. And if we want to know the value of any of these quantities at a specific moment in time, we look for the y component of those vectors. So this is everything for capacitors. And now we're going to talk about the last option we have here, inductor AC circuits. An inductor AC circuit might look like the following, with the inductance value being L and the voltage of the battery again being V0 times sine of omega t. And just like before, we're going to say that the voltage of the battery must be spent at the inductor and will therefore be V0 times sine of t. Sorry, times sine of omega t. But we also know from our formulas about inductors that we learned a little while ago that the voltage across an inductor as a function of time, or just the voltage across an inductor in general, is equal to the negative inductance times the derivative of the current with respect to time. So from this, we can then solve for this derivative, the derivative of the current, and that current is a function of time, with respect to time, gives you V0 over L times sine of omega t. So from this, we could take an integral if we needed to solve for the current as a function of time. and you end up with the following expression. That the current through the inductor as a function of time is negative V naught over omega L times cosine of omega t. And we're going to call this V naught over omega L. We're just going to call that I naught again. So we get negative I naught times cosine of omega t. And then again, we want to write this as a phase-shifted cosine. So the current through the inductor as a function of time, well, for a negative cosine, if a positive cosine was a pi over 2 phase shift, then a negative cosine is going to be a negative pi over 2 phase shift. So this becomes I naught times sine of omega t minus pi over 2 radians. Similar to before, we're going to define a quantity called the reactance for the capacitor, for the inductor. And this time it's going to be called the inductive reactance. And that will equal, again, it's defined as the maximum voltage in the inductor divided by the maximum current in the inductor. And that will turn out to be equal to omega times L. Again, like the capacitive reactance, the inductive reactance is measured in ohms and is basically about how hard the inductor fights any changes in current. We're not doing a whole lot with the reactances today, but they will be incredibly important for what we talk about on Wednesday. So do make sure you pay attention to those, even if they haven't been particularly useful so far. So now to try to figure out what the heck's going on in this circuit, we can draw our two graphs that we've been drawing this whole time. The plot versus time, and then eventually the phasor diagram. So for the versus time graph, we still have, try to make this a little nicer this time. We still have our voltage across our capacitor here, making a nice steady sine wave. So this is the voltage of the across the, not capacitor, the voltage across the inductor as a function of time with its maximum value V naught. But now our current through the inductor is a negative cosine, or a sine that is phase shifted by an amount of negative pi over 2, which means we took sine and we moved it pi over 2 to the right. So this 0 here becomes this 0 here, and we start off at a minimum. Starting off down here, passing through 0, hitting a maximum there, passing through 0, and so on. And this is the current through the inductor as a function of time, with its maximum value, don't do that, of I naught. Well, don't forget we have an expression for I naught down here. All of this is I naught. You can figure out what I naught is from the previous slide as well. So look at this and see if you can figure out which peaks first, the voltage or the current. And as time progresses to the right, voltage will peak here at this time, and then the current peaks later here at this time. So we can say here that the voltage peaks before the current. In an inductor AC circuit. So when we try to draw a phasor diagram, it should represent this same idea. So when we have our V naught vector pointing out here at some angle of omega t from the x-axis as this vector rotates around the origin at a speed of omega, then we can still say, well, the value of the voltage at any given point in time is the y component of that vector. Oh, that is not V naught. That should be the voltage across the inductor as a function of time. Well, now we still need to draw our current vector on here, but now the current vector shows up 1/4 of a period later at its maximum than the voltage does. which means the current will be down here. I naught from the maximum value, and then its projection onto the y-axis, or its y component, being the value of that variable, the current in the inductor, as a function of time. Where again, these vectors are going to be 90 degrees from each other, and both of them orbit around the origin at omega. So as we look at the y components of these vectors, the y component of the v0 vector will hit its maximum when v0 passes the y-axis. And then a quarter of a rotation later, then I0 will pass the y-axis and reach its maximum value. So just like in the above representation and the value of the graph of these functions over time, in the phasor diagram we also see that the voltage peaks before the current in an inductor AC circuit. So this is a lot, and it's a fairly new idea, but these are pretty kind of straightforward foundational ideas for AC circuits. That the voltage applied to the circuit is a sine wave as a function of time with some maximum value, and that a lot of our other circuit rules still work. All the voltage we get from the battery we must spend. Basically, in other words, Kirchhoff's loop rule still applies. Kirchhoff's junction rule will also still apply, but we haven't come into a situation where we needed to worry about that yet. And then we can still use Ohm's law for our resistor, Q equals Vc for our capacitor, and that the voltage of our inductor is negative L times the derivative of the current for our inductor. All of these things still apply, even when we're dealing with AC circuits. But how the circuit responds to the voltage will be very different. So, to try to help you remember which one peaks first, there is a mnemonic that is used sometimes, and it's called Eli the Iceman. Where Eli means that for inductors, the L standing for inductors in Eli, the EMF, that's the E in Eli, peaks before current, where current is the I. And correspondingly, Iceman is talking about capacitors, and it says that, or capacitors, which is the C in ice, and it says the current, I, peaks before the EMF, E. And then the only other thing you need to remember is that for resistors, the current and the EMF peak at the same time. Note that all of these EMFs are just the EMF of that particular circuit element. So this is saying, for the capacitor bit right here, the EMF is referring to Vc as a function of t. Or not Vc, VL as a function of t, since we're talking about the inductor here. And over here, for the capacitor, the EMF would be Vc as a function of t, and for resistors it would be Vr as a function of t. So I recommend trying to get comfortable with these phasor diagrams and exactly what information is contained on them, as well as understanding both conceptually and mathematically the differences between resistors, capacitors, and inductors and how they react to AC power supplies. If you try to kind of think through how the circuit reacts over time, you can do that with our current knowledge of what we know about capacitors, what we know about resistors, and what we know about inductors. But failing anything else, you should be able to at least describe the three of these circuits on phasor diagrams or on graphs of the quantities versus time, as well as telling me qualitative things like which values peak first, and being able to calculate things like currents and voltages at any given time, and the capacitive and inductive reactances. That's it for today. Thank you for watching, and have a good day.